Hi, welcome back. I'm Professor Ronald Vincent and Santiago, and today we'll be discussing Module 25, which is problems on Case 3, faults on power systems, loaded condition. Now, let us consider an unsymmetrical fault on loaded power system. This single line diagram as shown in the figure. So let the fault occur at point P as shown in the diagram. Notice that the transformers on the generator side is delta Y grounded, and at the motor side is Y grounded delta. Now here, let us consider the voltage at the fault point to be the potential voltage to neutral, the voltage before the occurrence of the fault. Then the positive, negative, and zero sequence networks of the system will be shown in this diagram. We determine the positive sequence network of that single line diagram with respect to the faulted point and the corresponding Thevenin equivalent circuit. And similarly for the negative sequence network and the zero sequence network. So under these loaded conditions, with fault on power systems, we can use the same formula in case 1. Unloaded generator, the only change being that EA or VG should be replaced by the terminal voltage BF or the fault point BF voltage with respect to the fault point. In case of a single line to ground fault, the short circuit current for this single line to ground fault, that will be equal to 3 times the phase voltage divided by the sum of the reactances, the X1, X2, and X0. So with this, it will now become IS short circuit, the short circuit current for this single line to ground fault, to be equal to 3 times the fault voltage divided by the sum of the network reactances, the sequence reactances. So note that the 3 times the value of the neutral impedance is eliminated because it will depend on the Thevenin zero sequence impedance of the network. Now, another example with regards to the figure in this diagram, the fault occurs at the primary of the transformer T2, and we need to compute for the single line to ground fault. So given this diagram, the fault point occurs at the primary side of the Y grounded delta of the transformer T2. So we have built the positive sequence network, and this gives us the value of the Thevenin equivalent impedance for the positive sequence network, measured between the fault point and the reference bus. And for the negative sequence network, this gives us the value of the Thevenin impedance, say TH2, with respect to the fault point and the reference bus. Notice that there will be no sources in the negative sequence network. For the zero sequence network, we need to consider how the transformers are connected based on the single line diagram as shown before. And from here, we can determine the Thevenin equivalent impedance for the zero sequence network measured between the fault point and the reference bus. Thus, for solving for the fault current for the single line to ground fault in per unit, that will be equal to 3 times the voltage at the fault point in per unit divided by the quantity twice the value of the positive sequence impedance, the equivalent Thevenin impedance of the positive sequence network, plus the value of the Thevenin impedance for the zero sequence network. So we substitute now the values, so that gives us 3 times the value of the fault impedance, fault voltage impedance in per unit, 1.0909, divided by twice the value of the Thevenin equivalent impedance of the positive sequence network, plus the Thevenin equivalent for the zero sequence network. So that gives us the fault current for the single line to ground fault in per unit to be 3.016, angle of negative 86.81 degrees. And solving for the base current, that will be equal to BB base over the square root of 3 multiplied by the say base, so that gives us 110 kV divided by square root of 3 divided by 121. So that gives us 524.86 amperes. So thus, we can now compute for the actual value of the fault current for the single line to ground fault by multiplying the base value to the per unit value. 524.86 multiplied by 3.016. So that gives us an actual value of 1,582.9 amperes. So that ends our module. So see you in our next module.